start with the topic of polygons here. If we're able to complete, polygons is not like a very huge topic, but yeah, if we can cover some theory of the circles, then it sort of takes off the load of the next Saturday. We can just directly then start with the questions of circles that week. But yeah, in any case, if even if the theory sort of gets pending for Saturday, we can start with the theory of circles there itself. Okay, so for polygons, right, and for triangles, we've covered like around more than 20, like 20 plus questions, right, and like all the questions were both like good quality and also CAT relevant, right, and we had done some CAT previous questions as well, and again like recent years questions because those tend to sort of resonate more with what they expect you to know. Okay, so starting with polygons, right. Now again, definitions and etc. Everybody knows, like, okay, this is like every figure is a polygon, every figure beyond the line is a polygon, right, basically. So every like after n equal to 3, n greater than equal to 3, every figure is a polygon. So triangle is a polygon with 3 sides, so n equal to 3. All the quadrilaterals are polygons with 4 sides, n equal to 4. Pentagon is 5, hexagon is 6, etc., etc. So everybody knows that, right. The first important formula for a polygon is the angle sum of a polygon, which is n minus 2 into 180 degrees. So for a hexagon, let's say it will be 6 minus 2 into 180, 4 into 180, which is 720 for a hexagon. For example, for an octagon, it will be 8 minus 2 into 180, so on and so forth. Now, angle sum, okay, this is fine. So if the polygon is regular, so there are two types of polygons, regular, irregular. For us, the more relevant one is the regular polygons, basically, where the sides and the angles are all equal. So for example, in case of a triangle, the regular polygon would be an equilateral triangle because all angles on all sides are equal. In case of a quadrilateral, the regular polygon would be a square, right? In case of a regular hexagon, we mean that if we draw a hexagon, all sides and all angles will be equal. So angle sum is this formula n minus 2 into 180 degrees, and each angle for a regular polygon will be n minus 2 into 180 divided by n. Obviously, because this is the angle sum, you have a total of n angles, so each of them would be n minus 2 into 180 by n. So this is each angle for a regular polygon. For an irregular polygon, we cannot say because the angles might be unequal. Okay, so this is the second thing. Now, if I give you the number of sides and ask you to find the angle sum, it is fairly direct. If I ask you to find the each and every angle of the polygon, regular polygon, again it is fairly direct, right? Now, so these things can vary with the number of sides. One thing that doesn't vary with the number of sides is the exterior angle sum, which is a very, very useful concept. Exterior angle sum of any polygon, irrespective of how many sides it has or whatever the, even like if it is regular, irregular, doesn't matter. The exterior angle sum will always be 360 degrees. Exterior angle sum, what do we mean by that? So basically, let's say we take a triangle, just take a triangle for the simplest case, and we can draw this for the figure as well. So let's say if this is 30, this is 45, this is 105, right? So this is not a regular polygon, right? Angles are different. But if we take the exterior angles of this, so this will be 150, this will be 75, this will be 135. You add these three, 135, 75, 150, you'll get 360. And in every polygon, the exterior angle sum would be 360. Okay, so this is pretty useful. And yeah, so these three concepts are basically like at the very basic of polygons. These three concepts are something that you should definitely know. Right. Now, how do we know when to use what essentially, right? So if they basically give you the number of sides, then everything is easy to figure out. Right. The sum of the angle, each angle, etc. is ready to figure out. You can even find out the exterior angle of each of them. Like exterior angle formula will always be 180 minus the interior angle, right? Because every time it will form a linear pair. So exterior angle is always 180 minus the interior angle. The sum of all those exterior angles will be 360 irrespective of what the polygon is, whether it is regular, irregular, whatever. Does not really matter. Every time it's always 360, and this is one result that we can use. We'll just go through an example where we use this. So if the sides are known, as we mentioned, we can find out the direct result. If the sides are not known, then the only thing that we can find out, the only thing that we know would be that the exterior angle sum would be 360 degrees. Like if we don't know the number of sides, then the only thing we know in that case is that the sum of, like, whatever be the case, the sum will always be 360 degrees. And this is a very important fact to know. Let's just do one quick question on this, right? So so there is this question, right? Angles of a convex polygon are in AP, and yeah, so to cover just between convex and concave, we just have a look with angles 100, 110, 120, and so on. So this is arithmetic progression with these angles and so on. What is the number of sides? So here we have to find the number of sides in the polygon, right? In our formulas, in our other, so all the other formulas were being derived from the number of sides. So there we always assume that the number of sides would be given. The only thing we know that is independent of the number of sides is the exterior angle sum. So we know that here that will only get used, right? So now it says that angles of a convex polygon are in an arithmetic progression with angles 100, 110, 120, etc. So exterior angle, we just saw that will be 180 because of the linear pair thing. So if we were to write the exterior angles for this, those will be 80, 70, 60, 50, so on and so forth, right? And we know that the sum of these can only be 360 degrees. So the sum of this AP should be 360 degrees. And basically, we just need to find the number of terms in this AP. That is what this question is about now, right? So we know the sum of the AP is n by 2, 2a plus n minus 1 into d. So basically, n is still an unknown. So 2a would be 2 into 80, which is 160, plus n minus 1 into d. D here is not 10 but minus 10 because it's a decreasing AP. So it will be n minus 1 into minus 10 equal to 720. 720 if we multiply to that side. So it will be n. So this becomes 170 minus 10n equal to 720. So the first catch in this problem was to sort of figure out that this, that this basically is a decreasing AP and the exterior angle sum, and that we have to use the 360-degree property. Right. So once you figure out this, then you figure out the concept. The second subtle part to figure out here is, do we really need to, if we open this up, right, it will give us a sort of a nasty quadratic, right, like 10n square, minus 170 and minus 720 plus 720 equal to 0. Now this is not an easy quadratic to deal. It will give you the correct answer definitely, but it's not an easy quadratic to deal with. So is there a quicker way to get the answer from this expression? Now typically this is also a variant of a problem that Cat has asked, but once you reach this stage, right, then the next catch is to like see that how can I make the calculation easier. Now all these will be integers, right? The number of sides will be an integer, this will be an integer. So basically this n will be a factor of 720, right? So just start testing factors of 720. The first factor is 1, but that will give me 1 into 170 minus 10, which is 160. This does not make it 720, so this is gone. N equal to 2. 2 is also a factor. So this will give me 2 into 170 minus 20, which is 150. 300, again this is not. 3 is also a factor. 3 into 170 minus 30, so 140, which is 420. Again not done. N equal to 4. 4 is also a factor of 720. So 4 into 130, this is, because 10 into 4. So this is also 520, does not give it to me. N equal to 5 is also a factor. So 5 into 120 gives me 600. Gets me closer, but not quite there. 6 is also a factor. 6 into 110, which is 660. Gets even closer, but not. 7 is not a factor. So we can skip that. N equal to 8 is a factor. Again, this is like lengthier to write down, but if you start doing it, it is just basically you're just putting in values directly here, right? An exam setup. N equal to 8 is 8 into 170 minus 80, which is 90, which gives me the 720. So N equal to 8. So the figure is an octagon. So again, if faced like in an exam, you just keep on just substituting these values here, and it is very fast to reach up to 8 basically. Once you see that, in for an educated guess, right? If you see that n equal to 2 only is getting up to 200, 300, and you still have quite a distance to cover till 720, you can just directly start putting n equal to 5 or 6 or some like bigger values, and then you'll eventually get to 8 quicker. So this could be a faster way to do it. Any questions? Yeah, and to discuss like the convex, what is the significance of it being convex? So basically, like in general, the polygons we deal with are always convex, right? Uh, Convex means that all internal angles are less than 180 degree. All angles less than 180 degree. Okay, and concave would be where one angle would be at least one angle. There could be more, but at least one angle would be greater than 180 degrees. So here the significance of giving convex was that all angles are less than 180 degrees. So you can compute exterior angles for them. Otherwise, the exterior angles will come out to be negative, right? Like if one angle is greater than 180, then exterior angle, like that angle itself will become an exterior angle, basically. So that's why. But in our scope, typically only convex polygons are there. So yeah. Now coming to some specific polygons that are asked, right, or have been asked, or like have featured in CATS, etc. So the first important polygon would be a hexagon. Like triangle, obviously we covered that itself is a polygon. Triangle is the most basic polygon. So yeah, that's covered. Hexagon is a six-sided figure here. And let's start our discussion with a regular hexagon. So basically all sides are equal. So now if I find the total angle sum, is 6 minus 2 into 180, which is 4 into 180, which is 720 degrees for hexagon. Each angle would be 720 by 6, which is 120 degrees. So each angle of a hexagon is 120 degrees for a regular hexagon. 120, 120, 120. Okay, now if I sort of join the like all the vertices right here, this is the point where the diagonals meet. So these are the diagonals that we've just joined, and obviously like this is 120, half of this will be 60, this will be 60. So this is to be, and so if this is 60, this is 60, so this will also be 60, the third angle of this particular triangle. Similarly, this is 60, this is 60, this is 60, this will also be 60. So essentially, it means that the hexagon, in case of a regular hexagon, is a collection of six equilateral triangles. It can be split into six equilateral triangles. Why equilateral? Because sides are obviously equal and all the angles are 60 degrees. Right? So important result, every regular hexagon is a keyword actually here. Every regular hexagon is six equilateral triangles. Okay. So basically the for the area, if we need to find, so every equilateral triangle has a side x. So every equilateral triangle will have a area of root 3 by 4 x square. So the total area of the hexagon will be 6 into root 3 by 4 x square for a regular hexagon. This is the area of a regular hexagon. There are a couple of things that you need to remember here for hexagon. You can see in hexagon, like here we sort of made the figure, like we made all the diagonals here, but you essentially you see if there's a hexagon, right, there are two types of diagonals here. One is a longer diagonal which like goes from one end straight to the other end, like AD, sort of the like a diameter sort of a thing, this one. And one is a shorter diagonal which is like this, right? So one is this diagonal, the other is this diagonal. And obviously if you have a question of, okay, you have not drawn like EC will be the same as AD, right? It's the same as the diameter sort of. Or you have not drawn FC is the same as EB. Like basically it is from the next to the next vertex. So from the next to the next vertex. So essentially there are only two types of diagonals here. One is a longer one is a shorter one. Right. Now the longer one can be easily figured out. This is an X, like this side was an X. So, and this is an equilateral triangle, so this will also be x, this will also be x. So the longer diagonal will always be equal to 2x. The longer diagonal of the hexagon will always be equal to 2x. The shorter diagonal, like we can derive it also, but just for this, so the shorter diagonal basically, if you need to find out FC from here, you know this angle, correct? This is 60. So you can, and you know this basically, you know this side, which is x. You know this side, you know this angle. You can use cosine rule to find out the shorter diagonal here, right? So the shorter diagonal comes out to be x root 3. Just keep these two results in mind. It can be easily derived, like this can be derived from the cosine law in any of these triangles basically, because like all the triangles are equal, and the longer diagonal is 2x. Also, like since we're speaking of diagonal side, there are actually two properties that we should keep in mind for diagonals of a polygon, and this will hold true for all polygons. So that for the diagonals of a polygon, right? So the total number of diagonals of any polygon, number of diagonals will be n into n minus 3 over 2. N into n minus 3 over 2. How to get this basically? So we know that in any, like how do we get diagonals? We get diagonals basically by joining any two vertices. In any basically polygon, let's say we draw a pentagon. So how do we get diagonal? Diagonal is basically joining any two vertices. So how many ways are there to join two vertices? Vertices NC2. But some of these combinations will be sides itself, because even sides are made by joining two vertices. You just subtract the sides. So NC2 is the total combinations, but this will be a sum of both diagonals and the side, because sides are also formed by combination of two vertices. So you just subtract the sides to avoid that double counting, and NC2 minus n will give you the number of diagonals. This, when you simplify it, it gives you n into n minus 3 by 2, because NC2 is nothing but n into n minus 1 by 2 minus n will give you this result, n into n minus 3 by 2 is the total number of diagonals. Now, this is a pretty common result, right? Like very standard, and people know this result. The next part of this is basically that how many of these diagonals pass through the center of the figure. Like for, let's say, if we have a figure that we relate to a square, so we know that there are two diagonals that pass through the center. If we have a hexagon, we know that there will be three diagonals that pass through the center. So basically the number of diagonals through the center, probably let's just write it on. So the number of diagonals through the center would be n by 2. Write it here itself, of any polygon basically. Number of diagonals will be n by 2. But the catch here is the two examples that we took, the square and the hexagon, both had, like, this has 4 sides, this has 6 sides. So both have an even number of sides. So this formula is only there for even number of sides. For even n, the number of diagonals that pass through the center is n by 2. Please keep this in mind. For odd n, the number of diagonals that pass through the center are 0. So if the question comes that, okay, there is a 14-sided figure, how many diagonals will pass through the center? The answer would be 7. If a question comes, if there's a polygon with 13 sides, how many diagonals will pass through the center? It will be 0. So even and odd is the only distinction here, and this is all you're basically supposed to know in terms of diagonals of polygons in general. For specific cases of the hexagon, as we saw, that the longer diagonal is 2x and x root 3. So please keep this in mind, the n by 2 and the 0 is by 10. So this is the sort of a discussion on hexagon. We'll discuss questions on this as well. But yeah, from a theoretical standpoint, this is the one. Okay. Now, if we take one more, if we take another special polygon, which is the last one, which is the octagon. 8-sided figure. Actually, this looks a bit complex, but it is even simpler than the hexagon, because there's only a very small couple of things you need to keep in mind, and you can derive everything from that. Right, now octagon basically, and again we are talking about regular octagons for now. So like, let's say each side is again x here. So now Anytime you see an octagon in a question, don't visualize this as an octagon per se. Visualize this as a square with ends that have been cut. So basically, if you have this sort of an octagon, this is basically a portion of a square. It's basically a square with the edges like cut. If you imagine a square paper, the edges have been cut and it gives you an octagon. So most questions of octagons can be dealt very easily by just visualizing the octagon as a sliced square. In terms of our usual parameters, like what is the angle sum? This will be 8 minus 2 into 180, 6 into 180, which is 1080. What is each angle? Will be 1080 by 8, which is 135 degrees. So every angle is 135 degrees. It is regular octagon, so every angle is the same. So these two are the typical parameters that we need to figure out. The one other parameter is that the area of an octagon is 2x square 1 plus root 2. X is the side of the octagon. And think about like why these people like gave question on an octagon at one time and not like a heptagon or a nonagon, etc. Because octagons are much simpler to reduce into familiar shapes. Like as we will see right now that how we can use the square fact, and 99% of octagon questions are dealt like that only. Like, it's not asked every year obviously, but like whenever it has been asked, the question is very easily doable visualizing it as a square. So for example, if I were to complete the square here, okay, this is a bit untidy, maybe completing the square here, so every side is x, and this angle is 135 degrees. Now, if this is 135, this is 45. This is equal to this. This is equal to this. This is 45. This is also 45. Basically, this is 45. This is 45. This is 45. This is 45. And similarly here, this and this would be 45. Right. To say that basically, and again, how to get this 45 is simple because all angles are 135, so this is exterior angle. Now, what does this tell me? This tells me first of all that an octagon is nothing basically but this, like at the corners we have these right angle isosceles triangles. So let's say this is x basically, right? Like this x basically, this is also x, regular octagon, and this is a right angle isosceles triangle. Why? Because 45 45, right? So if this is x, then this would be x by root 2, this would be x by root 2, similarly this would be x by root 2, this would be x by root 2. So really the square that we've been talking about, right, the side of that square becomes x plus x by root 2 plus x by root 2 is x plus x root 2, or x into 1 plus root 2. Again, we'll do a question also, but any octagon can be visualized like this. Side of the octagon x, right angle isosceles triangle, x by root 2, x by root 2, and the side will be the sum of this portion, this portion, this portion. All sides will be the same. Okay. So this is a very important this thing that it can be visualized this way. Somebody has a question? So this is basically an octagon, and yeah, so octagon in any type you should always try to visualize it as a collection of, even like, okay, this was like for the outside part of it. Even internally, if you see, it's nothing but a collection of rectangles and right angle isosceles triangles, right? If you were to draw an octagon here, and if I like again make all these lines basically here, right? So what is it? This is a rectangle. This is a isosceles right angle triangle. Why? Because like this is 90, 90, 90, 90. This will be 45. Why? Because total is 135. This is 45. This is similarly 45. So the entire octagon is a collection of rectangles and right angle isosceles triangles. So as you would have recalled, right, in the question we discussed that whenever you have questions on area, etc., or even in general, it's always easy to break down the diagram into figures that we know or are comfortable with. So this is the thing for the octagon. So you can visualize it by breaking it down into this way, rectangles and right angles and this triangles. And let's do a few questions on this to basically have this into better perspective. So in a regular octagon, A, B, C, D taken in order, you can choose basically any order. Each side is 10. Find area A, B, C, H. So this area we need to find out. 10, 10, 10 we know. Like we only need to focus on this area. Again, as we just saw, you can break this up here. Perpendicular, perpendicular. So if this is 10, this would also be 10. Rectangle. And this is 90. This is total is 140, 135. This is 90, so this is 45. Again, as we saw, right angle isosceles triangles being formed. 45, 45. So this is 10 given. So basically, if this is 10, this would be 10 upon root 2, just using basic trigonometry, or if you remember the right angle isosceles of 1 is to 1 is to root 2. So similarly, this is 10 by root 2, this is 10 by root 2, this is 10 by root 2, this is 10 by root 2. So basically, this figure is nothing but a collection of this rectangle and these two triangles, or actually directly you can call it a trapezium. This entire piece is a trapezium. Why trapezium? Because the sides are, one pair of sides are parallel, the other sides are not parallel, right? So, and the area of trapezium we know is half into sum of parallel sides into height, into height. This is the area of a trapezium. Here the parallel sides are 10, and this entire side CH would be, what would be CH equal to? So this is 10 plus 10 by root 2, again deriving using trigonometry, plus 10 by root 2. So this is 10 into 1 plus root 2. So sum of parallel side would be 10 plus 10 plus 10 root 2. This is one parallel side, this is the other parallel side, into height. Height of the trapezium is what? Height means the perpendicular distance is 10 by root 2. You can find this out. 20 plus 10 root 2 into 10 root 2. 10 by root 2 actually. Right. You can basically just find it out. 10 by 2 root 2 into 20 plus 10 root 2, and yeah, if you want to basically rationalize this further, so it will be 50 root 2 plus 50, so it is 50 into 1 plus root 2 is the area. So basically, after this point is just arithmetic, but this is the point that you need to just get to, just figuring out in this, and it was pretty simple, right? Just basic 90, 45, 45 stuff. So you can figure out these sides, and we actually, this particular thing we did in the theoretical explanation as well, that this side would be this plus this by root 2 plus this by root 2, so it should be okay. Okay, coming to hexagon. In a regular hexagon, A, B, C, D, E, F, A, B is 3, B, C 5, C, D 4, D 5. This question would be pretty useful because it sort of illustrates a very common principle that we use in hexagon questions. Right, now, some of the questions, like we saw that, right, that the longer diagonal is 2A for a side of A units, and the shorter diagonal is A root 3, etc. There might be direct questions on them. Like, don't be surprised if you find direct questions on them. But this question, like this question was pretty useful, right? To to see that, okay, how to visualize this. This question would be useful to sort of illustrate an application of a certain method. So this is a hexagon, right? And we know that, okay, if we just were to name this A, B, C, D, E, F, 3, 5, 4, 5. Now we need to find the area of the hexagon. So the first thing to catch is, we know what the area of hexagon is, 6 into root 3 by 4 A square. But the thing is, that is for a regular hexagon, because only in a regular hexagon you would have those equilateral triangles internally, and you can just calculate area of one and multiply with 6 to get 6 into root 3 by 4 A square. Here the sides are clearly different. How to find the area? And also, even in that, like, all the sides are not known. So how to find the area? So here, and it's a standard approach, so which is why the question was useful. So basically, you know that each angle in a hexagon is 120 degrees. 120, 120, 120, 120 everywhere. So essentially to say that for every angle, the exterior angle would be 60 degrees.
Hello.
Hello, yeah.
Actually, so if as the sides are not equal, it should not be a regular hexagon, right?
So, okay, basically the thing is that a regular hexagon can be like if either of those two things are equal. If both are equal, then it will obviously be a regular hexagon. But even if like sides are unequal, it can be called a regular hexagon because the angles in this case that is why they gave in the question that it's a regular hexagon because to for us to conclude that the angles would be equal even if the sides are not equal.
Oh,
So
okay.
in a question, if you see this, if both are equal, then yes, then it's sort of the more simplified case. But if
Okay.
you see regular and sides are unequal, you should conclude that the angles would be equal in this case. So 120, 120 and everything, and then the 60, 60 exterior angles. Now, what value do I get from making these exterior angles? So basically the value is that if I sort of extend these two sides to meet somewhere, right, like this and this. So this is 60, this is 60. So obviously in this triangle, and they will obviously meet because they are non-parallel lines, right? So this will also be 60. So which tells me that this is an equilateral triangle. Similarly, I can draw from other side as well. Like let's say this is 4. This is this. If I draw this triangle, so this again will be 60. This is 60. This is 60. So 4, 4, and 4. Why 4 and 4? Because equilateral triangle. So on every branch, we can do this. So now what use does this have? So if this is 3, this will also be 3. This will also be 3. Right? If I do the same thing here as well, right? 120, so this is also an equilateral triangle. So we don't know this side. But let's say if this side was x, for example, so this would also be x, this would also be x. We know 3, 5, 4, and 5. Yes. Right. So basically, like we so essentially what we have done is we have converted this figure into a very big equilateral triangle because this was also 60. So if you see that this big equilateral triangle, all angles are 60. 60 here, 60
So,
here, 60. Yeah.
so it is very similar to octagon where we can imagine the square, and in case of hexagon, we can imagine an equilateral triangle.
Yeah.
Or
There the only
middle triangle.
difference is yeah, absolutely. There the like the only difference being that there like you didn't need to do any construction also. Here you have to sort of extend this to sort of visualize that. But yes, if the angles are equal, and again, all of this is based on the fact that the question mentioned regular, so we knew that even if the sides are not equal, the angles will be equal. So 120, 120, and this is what gave us the 60, 60, 60 that make the equilateral triangle. So, but yeah, once that is there, then you can visualize it at a sort of a cut version of a bigger equilateral triangle. So now we know that okay, 60, 60 makes an equilateral triangle, then fine. So in this equilateral triangle, we know like we don't know these sides, right? Like even this side we don't know. This would have also been an equilateral triangle. If this is y, let's say whatever. Similarly here also, but yeah, basically like this is a bigger equilateral triangle. So we know the three sides here, 3, 5, and 4. So we know that the side of the bigger equilateral triangle is nothing but 3 plus 5 plus 4, which is 12 units. So we know that this entire side is 12. So this will also be 12 because equilateral. So this is 4, this is 5, 5, this should be 3. This is 3, this is equilateral, so this is 3. Right? Similarly, now this basically this side will also be 12. So this is 3, this is 3, so this will be 6. So basically we figured out all sides of the equilateral or all of the hexagon now. So it is 3, like this was given, this was given, this was given, this was given. These two we have figured out because of the equilateral triangle side of 12, and using just basic like okay, we know two portions of it, the third portion can be figured out. Essentially the portions that we needed were only actually, if you think about it, were only right. Now we need to find the area of the hexagon. So clearly the area of the hexagon is area of the bigger equilateral triangle minus the area of three smaller equilateral triangles. These are also equilateral, 60 to 60 each. So these can also be like derived using equilateral formula, and the bigger equilateral triangle formula would be root 3 by 4 into 12 square. minus this will be root 3 by 4 into 3 square, root 3 by 4 into 4 square, root 3 by 4 into 3 square again. This is, you can take basically root 3 by 4 common and then basically have 3 square plus 4 square plus 3 square, so which is 9 plus 9 plus 16, this is 34. So it is root 3 by 4 into 144 minus 34, which is 110. So this would be your answer. So hopefully that makes some sense in terms of solving these kind of problems. Again, polygons not a very huge topic, but yeah, just good to know some of the principles and like some of the standard methods. Cool. So this is basically done. The next polygon basically that we're going to look at is another important one, which is the last one, which is called the trapezium. That actually used to give a question on trapeziums every year, like one question would come or something like that. So even in CAT it has appeared. We'll solve the CAT ones as well.